So in the video on the ratio test, we had looked at this series right here, and the ratio test was inconclusive because the limit of successive terms of the sequence was equal to 1. Can we think of another way to determine if this series converges or diverges? Well, we have a few things we could think about. First of all, we could ask, is it geometric? Well, the answer is pretty clearly no. Remember, geometric, you need to be multiplying by the same thing each time. Is it a p-series? Well, no. P-series would be, 1 over n to the p. It looks kind of like 1 over n, but it's got this negative 1 to a power, so it's going to be alternating in some ways, so it's not a p-series. Could we do comparison? Well, the problem with comparison is you need things to be, positive so that they could be less than something that converges, but also greater than 0. So comparison doesn't seem to work. Limit comparison might work, but then you'd be comparing it. No, I think limit comparison things need to be positive as well. Yes, they do, so that's not going to work. The ratio test didn't work, so we're kind of out of options, which is why we need a new test. So the alternating series test basically says if you have a series that alternates, so this little negative 1 is going to make things go positive, then negative, then positive, then negative, then positive, then negative, etc. It converges if the limit as n approaches infinity of a sub n equals 0. So that's the positive part, right, of this sequence. And the reason that we only need this thing to go to 0 is because when these things alternate, a lot of the negative terms are going to eat up the positive terms. We saw this earlier. And so because all those positive terms and negative terms are eating each other up, it just has to approach 0. It doesn't even have to approach 0 that fast. So this is a very straightforward test that we can apply to see if something converges or diverges, so long as it is an alternating series. So let's apply that to this example 7, which was also example 6 on the previous page, by the way. So basically, we have an alternating series. This is equal to the sum from n equals 1 to infinity of negative 1 to the n minus 1 times 1 over n, right? If I pull out the negative 1 to the n minus 1, I just have negative 1 to the n minus 1 times 1 over n. So in this case, the a sub n is 1 over n. So I need to check to see, does the limit as n approaches infinity of 1 over n equal 0? Yes. It definitely equals 0. And so I know that this series converges. Now, let's remember that this diverges, but this converges. So this is the harmonic series, and it's a divergent p series with p equal to 1. But this is a convergent alternating series. So if you think about this, this would actually be 1 plus 1/2 plus 1/3 plus 1/4 plus ... But this would be, let's see, if we plug in 1, we're going to get positive. So 1 minus 1/2 plus 1/3 minus 1/4 plus 1/5 minus 1/6 plus ... So because we're adding and subtracting, our sum is going to be much smaller, and so this converges, but this diverges. All right, let's look at this one. So this again is an alternating series because we have negative 1 raised to a power, and now we need to look at this positive portion and see if the limit equals 0. Well, the limit as n approaches infinity of 1 plus 1 over n squared equals 1 plus 0, which equals 1. Well, that basically means that this thing right here, right? The limit of this sequence doesn't equal 0 either, right? The terms here of this sequence are -1, 1, -1, 1, -1, etc. At least as n approaches infinity, that's how it's going to behave. So we know that if the sequence doesn't approach 0, this whole series has to diverge. So this series diverges. Okay. So one more definition here is absolutely versus conditionally convergent. So we say that the series is absolutely convergent if both the series n equals 1 to infinity of a sub n and the series from n equals 1 to infinity of absolute value a sub n converge. That means that basically an alternating series doesn't depend on the alternating stuff. So this one right here, it does depend on the alternating business to converge, right? If we took the absolute value of this, we would get this, and that diverges. So absolutely convergent means that they would both converge. Conditionally convergent if we need the alternating stuff. So this converges, but this diverges. So just as a final example here, let's think about this one, which we just looked at. This is conditionally convergent. Since the absolute value of this, which is just the harmonic series, diverges. But consider -1 to the n minus 1 over n squared. This is absolutely convergent since the sum of 1 over n squared converges. So this harmonic series needs the alternating portion to converge, but 1 over n squared is a convergent p-series, so if it alternates, it will simply converge faster. So to summarize, the alternating series test works on alternating series, so obviously it has to be something that alternates between positive and negative. If the positive part approaches 0, then it will converge. Meaning if you take the absolute value of this and it approaches 0, then it will converge. If not, then it won't. So I guess we could say converges if this, diverges otherwise. Then absolutely versus conditionally convergent, something is absolutely convergent if both the series and its absolute value converge, but conditionally convergent if it needs the alternating business to converge.